So I'd like to now take a look at this present value equation, and let's give an example as to what we're talking about so you can see how we'll manipulate this equation. Let's assume for a moment that we have someone that says, hey, I would like to give you $1,000 in the future, and I want to do that in exchange for some amount of money today. Well, okay, that's saying we're going to pay you $1,000 in the future, maybe against a loan of some amount of money today, and we're going to use some kind of an interest rate. So I'm going to think about this as my beta as 1,000. My R is my interest rate, and let's call that 6% or 0.06. I'll think about time in this case, and I'm going to consider time very simply. I'll consider time is 3 years. And then I want to solve for present value. So this equation would be present value is equal to $1,000 divided by 1.06 to the third. Well, 1,000 divided by 1.06 to the third is $839.62. $839.62. If someone said, if you'll loan me $900 today, I will give you $1,000 in the future, you would then be able to calculate and say, I don't like that so much. That doesn't give me my required rate of return of 6%. Or if they said, I would like to pay you $1,000 in the future against some loan today, I need $839, you could calculate this and say, that equals a 6% rate of return. And you could decide that that's good, or maybe you decide it's not good. Okay? What if we've got someone that says, I'd like to invest $1,000 with you today. And in exchange for that, I would like you to give me $1,200 back in 5 years. And in 4 years. And we're going to think about this with an interest rate of 5%. So 1.05 to the fourth. Well, here we're changing our variables now. And we've got a variable of 1,000. We've got beta, or our future cash flow, 1,200. We've got our rate of 5% or 0.05 and time of 4. Does that make sense to us? It does. 1,000 today is equal to $1,200 in 4 years at 5%. So that makes sense to us. We're willing to do that, perhaps. Or maybe it's a little bit different still. Let's now think of when we have a scenario in which we've got $500 today, $700 in the future. We don't know the rate, but we know the period is 3 years. Can we solve for the rate? Well, we can, and we'll do it like this. 500 is equal to 700 divided by 1 plus r to the third. We can go ahead now and we can rearrange the equation. I'll multiply both sides by 1 plus r. So 1 plus r to the third, I'll multiply them by 1 plus r to the third, times 500 equals 700. Now we'll go ahead and divide each side of the equation by 500. 1 plus r to the third equals 700 divided by 500, which I believe is equal to 1.4. And now I want to go ahead and get rid of the exponent. Well, I can go ahead and take both sides of the equation to the third root. When I take this to the third root, it's 1 plus r to the 3 divided by 3, being equal to 1.4 to the 1/3. You might sometimes think of this as 1.4 to the third. It means the same thing. Well, what is 1.4 to the third? Well, 1.4 to the third is 1.1187. So I've got 1 plus r now being equal to 1.1187. I'll subtract 1 from each side, leaving me with r is equal to 0.1187. So there are a number of things we can do here. We can go ahead and even solve for the time exponent. To do that, we're going to think about taking a natural log. So let's consider a different equation where we know present value, beta, rate, but we don't know time. Let's say that our present value is equal to 100. Our cash flow or future value, in this case because it's a one-shot transaction, is equal to 150. Our rate is equal to 6%, and we need to solve for time. How would we do that? So let's set up the equation. 100 is equal to 150 divided by 1.06 to the t. I don't know what t is. So I'm going to rearrange this algebraically such that I'll end up with 1.06 to the t is equal to 150 divided by 100, and that's equal to 1.5 or 1.50. In order to solve this, I need to apply a natural log here. And applying a natural log to each side allows me to move the exponent down as a scalar in front of the equation. So if I apply the natural log to this, I'm going to end up with t ln times 1.06 is equal to the natural log of 1.50. And now I can divide both sides by natural log of 1.06 such that I have t is equal to ln 1.50 divided by ln 1.06. Well, the natural log of 1.5 and the natural log of 1.06 are just numbers. In this case, they happen to be equal to 0.4055 divided by 0.05827, which equals 6.95, which equals our time factor. So here we've taken a look at using this one somewhat simple equation, and we've just looked at a few different scenarios with it just to show you that you can have the equation and solve for any one of the variables using some algebraic functions. Let's do the same thing now, give an example, using the future value equation. Let's assume that we want to find the future value. We know that the present value is going to be equal, in this case, let's say that it is 15,000. And let's say that R is 7%. And let's say that our T is 10. And we want to know what the future value is. We've been solving for the present value. Now let's solve for the future value. And we'll go ahead and say 15,000 times 1.07 to the 10th is equal to some number. Well, that's going to equal 29,507.27. And just like we did with the present value calculation, as long as we have all but one of the variables, we can solve for the other variable. And recognize in this case, both for the present value and the future value, we've had another variable here that may or may not have been expressed, beta, but beta has been equal to future value, so we don't need to have every one of these specified for us. We just need to know that we've got at least 4 of the 5 variables. And in this case, I had 1, 2, 3, and 4 was beta was equal to future value, and I could solve for future value. Or I could have had future value, present value, rate, and solve for time, or I could have solved for R. And in this case, I think of this as 4 variables, but really it's 5 because beta and future value have been the same.